Let's talk about amplitude, frequency, and phase. For any periodical sound, and that means the sound that has its properties unchanged through time, we could decide on its constant frequency, on its constant phase, and its amplitude. Those three don't have to be constant, and most of the sounds in nature don't have those three as a constant value. Considering that we are going to be dealing with sound design and synthesizers, we have to start with the constant so you could grasp these three values. So the amplitude, frequency, and phase. Now let's start with one of these, with the first one. I'm going to play you this sine wave, obviously, and show you what that sounds like. Now you hear that propagating. As these values change, so does our speaker move. And you could have seen that in our number 1 course called Digital Audio Workstation. We went through these. Now, going through the frequency, so you can see that one of these always, the signal going down and going upwards, going down back into zero again, is one oscillation. One oscillation. Now, if that happens once every second, that means that the frequency is going to be 1 Hertz. So one oscillation per second is 1 Hertz. Now, the higher the frequency, the higher the pitch of the sound. You heard this one. Now let's hear what the double frequency of that is going to sound. You see, this one makes 2 oscillations, while the upper one makes only 1. Let's hear the next one. So the frequency of that one is twice as high. Now let's see twice from that one. So this is 4 times faster oscillation than the initial sine wave I played for you. And now double of that again. So this is 8 times faster than the first one. The higher the frequency, the higher the pitch of the tone. So the frequency is defined as how many of these oscillations, so from the balance from 0, going negative, going positive, going back to 0. It could be from, let's say here, going positive, going negative, and then coming back into 0. That's one oscillation. How many of those in a second equals frequency? Now, frequency decides on the pitch of the tone. We also have amplitude. Now, we could change the amplitude of this tone to go higher or go lower. So see, if I change the amplitude for higher, it's going to be louder. If I change for lower, and even lower. So the amplitude is the strength of the signal, the loudness of the signal. So those two come in hand. Now, if you watch our DAW course, Digital Audio Workstation course, you'd have seen the detailed explanation for this. Going through the amplitude and the frequency, those are the 2 values we have. The horizontal is the frequency, the speed of the oscillation, and the amplitude, which is the vertical. So the sound, loudness, the strength of the sound, the strength of the signal. Now we also have another value, and that's phase. Phase would mean moving this one in time. So the sound would not start at 0. It would start here, or it would start here, or it would start there. Now to our ears, that all sounds the same. So if I play the sound like this, or I start the sound from here, it sounds the same, it doesn't matter. But what if we had 2 of these sounds combined? So what if I had the first one and the second one playing together? Now let me lower the volume of these 2, since adding them up will make for double of the volume, of course. And lower this one down. Okay. Now once we have those 2 set, let's see what they sound like together. Now we have those 2. Now let's see what they look like when they are playing together. So what does the combined waveform of these 2 look like? I'm going to make another audio track. And I'm going to record whatever's coming out of these 2 into this audio track. So let's try that. Sampling these 2. Okay, so let's record a bit of that, just a portion. Now this is the combined version of those 2 waveforms. Let's discard these two so they don't confuse you. So you can see these two. Now the combined version is adding amplitude values for each one of these points in time, and we get a combined waveform for these two. You see what that looks like? Yeah. Now, if we change the phase on one of these, so just moved it in time a tiny bit, we would get a different result than this. So I'm going to make another audio track, and we will record that too. So now we're recording those two again, but with the phase moved. Just to see what's going to happen, I'm going to change this to resampling to record the output of whatever we hear. So let's go. Now stop it. Now let's see the differences between the first recording and the last recording. As you can see, we recorded from the same spot in time, but they are not the same. This one goes down there, they're not exactly identical, although we did record two identical signals and they do sound identical. Let me play this for you. So they do sound the same, but they are not the same. You see, this one goes kind of downwards, like a bigger hill, lower hill, bigger hill, lower hill. And this one goes lower, bigger, lower, bigger. Now that gets even more complicated once we have more than two sounds combined. So let's say we combine these three sounds like that. 1, 2, 3. Now I'm going to record these three together. Let's see what that sounds like. Just -6. Now you see we have these three recorded just like that. Now let's move the phase of one of these like that and move the phase of this one like that and see what we're going to get now. So I'm going to create another audio track. I'm going to record these three, but with phases moved of these two. So let's see what that's going to look like. Now you see these two sound waves are not the same. They are quite different. You can see that we have a dip here, we have a hill right there. So moving the phase does actually affect the way the waveform is going to come out like. Now for us, it might sound the same. You can maybe, with a trained ear, hear slight differences in harmonic content between these. Now, since they are only sine waves and they have only one harmonic, which we are going to go through in detail during this lesson on waveforms, the only difference you need to notice here is that changing the phase, changing the movement of that oscillation, when does it actually start and stop in time compared to the others, actually matters for the end result and for the sum of maybe a couple of different sounds being summed up together. They sound the same, but they are not the same. You see that this is not the same waveform. So moving the phase is going to ultimately change which values align together and need to be summed up together into a new wave file. Because what I have here is just a sum of these three together. This is what they would look like. So combining three very simple waveforms like that, we get a more complex one. This is how music ultimately works. This is how sound design actually works. We're adding sounds together and we are getting something more complex. Now, we do not always work with sine waves, as simple as this really looks, but the important thing from this lesson is the frequency, so the speed at which a sound is oscillating, the amplitude, so the loudness, the strength of the signal, the loudness of that sound, and the phase at which that sound is starting. It might not be starting always from zero. It might be starting from somewhere else. Let's see an interesting case, which I think I've shown you in the lesson before, and that's if we had two of the same, exact same signals, like this one. Let me close out the other ones. So we have two of the same signals. I'm going to move them all the way downwards. and they are in the same phase. So if I add those two together, I'm going to make a new audio track and record those two together. Let's see what I'm going to get. So solo, solo. I'm going to hear only these two. I solo them. So let's record that. So see, what I got was the same signal. It's just twice as loud. And believe me, it would be if these were set to 0. So let me demonstrate that for you. So you see, what I got was the same waveform because these two are identical and they are completely in phase. So I'm getting the same signal but twice as loud. And twice as loud would be 6 decibel louder. So this is twice as loud as these two. But what if I change the phase a little bit? So let's create a new audio track that we're going to record onto. And let's change the phase of one of these. Like so. It doesn't have to be completely opposite, but let's try. Now let's try to make it completely opposite. So wherever there is a hill right here, we're going to make a dip right there, and vice versa. So let me try to be even more precise, just like that. Let's see what that's going to come up with. And you will hear the difference immediately. So again, recording. So you see what we got now? Disregarding this beginning where we don't have one of them, actually. When you look at this result, the end result waveform, we got the same one, but it's so much quieter. You see that? Because they are in the opposite phases. If I manage to align this perfectly, wherever there is a maximum hill right there, we have a maximum dip down there, we would get complete silence. Let's try that with this movement now. You see almost complete silence. So moving the phase between these two really affected the end result I'm going to get. Because if I'm just adding the amplitude values of these two signals, of course, if this one is at maximum, this one is at minimum, and vice versa, and they are completely identical, just opposite phase, we're going to get 0 signal. So nothing, almost nothing. See that? If I manage to align those perfectly, hills and these valleys, if I manage to align those perfectly, I would get complete 0. And I showed that in the digital audio workstation part of the course, explaining the phase cancellation. Now, why do we go through all of these? Well, phase is going to be really important for sound design. Now, each one of these is a different note. So when you play music and you play different notes, this is how they differ. They differ in frequency. So let me explain that using a synthesizer. I have this serum right there. I'm going to open it so you can see it. And I'm going to open an oscilloscope. So you can see the oscillations moving. Of course, it's always going to be a sine wave, just like this one, but you will be able to see the end result right there. So you see, that's a low one. Let's do a higher one. See, it's faster. More oscillations in a unit of time. Even higher, lower, lower. That one is so low, you don't even hear it. Anything below 20 Hertz, so anything below 20 oscillations per second, you don't actually hear. Why? Because human ears are not made to hear anything below 20 Hertz, so 20 oscillations per second, or anything above 20,000 Hertz. 20,000 oscillations per second. And that is just the limitations of our human listening apparatus. Now, you know those whistles for dogs that when you blow into them, nothing happens. I mean, you don't hear any sound, but dogs get freaked out. That's because they hear the frequency from that. They hear higher frequencies than we do. We don't. So we are actually producing sound that we can't hear. It is the same thing as light. There are certain wavelengths of light that we see, starting from red all the way up to violet. Now, infrared, lower than red color, we don't see. That is why when you point a remote onto your TV, you don't see it flashing any light from that, LED diode. But it is actually flashing light. It's flashing infrared light that you don't see. This is because our eyes, our viewing apparatus are not made to see any light in a frequency lower than red. Also with the ultraviolet, we don't see anything in higher frequency of light and color than violet. So we don't see it, but we see the effect it has on fluorescent colors. Now, there are many more frequencies in the light spectrum, like X-rays, that we don't see. They do exist. They are right there. The radiation from the sun, we don't see it. It's right there. The same goes for the sound. So we only hear a limited piece of the sound spectrum, from 20 Hertz to 20,000 Hertz. And that's all. So if I went higher than 20,000 Hertz, we wouldn't hear it. Now that's for a really healthy young human. The older you get, you are starting to lose the higher frequencies of your hearing. Now we can go back to the synth and I can show you this sine wave in action. So very low, higher, and I can change that frequency by just playing a different note. Or I can change it gradually using the pitch bend modulation wheel, which we're going to be talking about. See that I can manipulate the frequency of the oscillator. And you can see the end result on the oscilloscope. So higher tones have higher frequency, lower tones have lower frequency. And I can do the same thing with the amplitude. Actually, the level of this oscillator is going to be the amplitude of this oscillator, of this sine wave. So look at the oscilloscope as I change it real time. What we can't see is the phase change. And that marks where is it going to start from. So every time I play a note from the beginning, is this signal going to start from this point onwards and looping like that constantly? So I can choose if I'm going to start from the valley, the hill, the zero crossing, somewhere in between. And all of these help us shape the sounds when we deal with sound design. It's very important to know the three basic and most important characteristics and values of a signal. And that is frequency, the speed, amplitude, the strength, and phase at which it is starting from.